The maths A-level specifications in England talk about two-dimensional vectors and three-dimensional vectors, but I love to teach one-dimensional vectors as well, and there are a couple of reasons for that. As mathematicians, we always like to look at the simplest, even trivial cases of new ideas, because it helps to ground the new ideas in the old ones that are familiar. So in this case, it'll teach us how vector arithmetic generalizes ordinary numeric real arithmetic. The other way around is almost more important in this case, because people's intuition about numbers and vectors can actually be quite different, even contradictory. And applying vector thinking to ordinary number arithmetic can help to strengthen people's intuition about numbers and make it more versatile. So let's go. So what is a vector? Well, we think of a vector as either a column of numbers or an arrow in space, and it can be a column of three numbers in three an arrow in three space, a column of two numbers and an arrow in two space, or a column with just one number in it and it's an arrow in one space. And of course they can go in all sorts of different directions, including with negative numbers and things. Well, I think the difference between one dimensions and the higher dimensions is that direction is binary. It's either positive or negative, whereas in the higher dimension it's continuous and can go anywhere. And that's one of the reasons people's intuition about numbers and vectors is different, I think. The other one is a very different point in their mathematical careers where they first meet them. So most people meet the idea of numbers before they even get to school. They don't meet vectors until right at the end of their school career. So, and one of the things we have to remember about vectors is that they move around, in the sense that the information content of a vector doesn't tell you where it is because it isn't really anywhere. So if you move them around, they're still the same vector. Okay, so let's think about addition. So vector addition we see here uses ordinary number addition, but it also generalizes it in the sense that one-dimensional vector addition is just number addition. And if we look at the arrow version, this is a very appealing picture that students typically get hold of very well and they enjoy it. So here's adding the blue vector to the black one, however many dimensions, and you move the tail of the blue arrow to the nose of the black one, and then you trace out both both journeys to add them. Now I don't think that's necessarily the way people normally think about adding numbers, but actually it's rather a good way to do so, especially if negative numbers are involved. So just look at the one-dimensional case, moving the -6 so that its tail is at the nose of the +4, and then adding the two together by making the two journeys. That's a nice way of thinking about it, I think. Okay, negating vectors. Again, we see that negating a vector uses the negation of numbers, but it also generalizes it. In the negation of a one-dimensional vector is essentially just the negation of the number involved. And again, the arrow picture of this is also very appealing. You just reverse the arrow to make the journey backwards. And again, I'm not sure that people necessarily think about negating numbers that way. But it's a nice way to think about what is the negative of -4. Well, turn the arrow around, and it's 4. Subtraction for vectors. Well, a minus b is defined to be a plus minus b, negative b. That's not at all how we learnt about the subtraction of numbers, is it? Where we started subtracting small positive integers from larger positive integers. And that leads to the hopefully temporary intuition that subtracting something from a number always makes it smaller. But some little shadow of that intuition can linger on for years, and people still sometimes feel a little bit uncomfortable about sums like this. They can generally follow the procedure that gets the right answer, but I don't know that their intuition gives them a terribly good feeling for why that procedure gives the right answer. And again, thinking about one-dimensional vectors can help here. So subtract the blue arrow from the black arrow. We first of all reverse it, move it tail to nose, and then add it. And again, it's not necessarily how people think about subtracting numbers, but it's a very good way to think about it. Here is subtracting -2 from 4. So you first of all reverse it, then you move it tail to nose, and then you add. And that's a nice way to think about that, I think. Scalar product. Again, we see that the scalar product of vectors uses the product of numbers, but it also generalizes it. And here, the scalar product of two one-dimensional vectors is essentially the product of the two numbers. And the modulus is rather cute. So the modulus of a vector is the sum of the squares of its coordinates. So in one dimension, it's just the square root of a squared. That's rather nice. And this is, of course, also modulus of a, where modulus now is the function that we also study at A level. So applying vector thinking to that tells us we can think of the modulus function as the size of a, and that also tells us we can think of, for example, as modulus of a minus b as the distance from a to b, as numbers, that is. But thinking of the modulus as the square root of a squared is really rather cute. So you know that one of the ways you can solve equations involving the modulus function is to square the equation. And I used to think that was a bit of a kludge, a bit ugly really. But actually, if you think of the modulus function as the square root of a squared, then squaring the equation is the most natural thing in the world. So I like it now. Going back to the scalar product, but now using the modulus function, of course, in one dimension, cos theta is either +1 or -1. And so vector thinking here can reinforce the right intuition for why the product between negative numbers is positive. If we look at in two dimensions, here we have the product of two vectors, one of length 2 and one of length 3, pointing in the same direction. And well, wherever they point, it's perfectly natural to think that their scalar product is always the same, and that it's 6. But if you stop it there, well, it somehow seems less natural that the scalar product of 2 and 3 is the same as the scalar product of -2 and -3. Excuse me. But actually, vector thinking again gets that right. So I said right at the beginning that we like to look at the simplest, even trivial cases. Well, one-dimensional vectors are not a trivial. One-dimensional vectors are the simplest, non-trivial case of vectors. Are we to make any sense of zero-dimensional vectors? Well, let's look at that. So, as a column of numbers, it's got no numbers in it. It's got no coordinates, so it looks like this. Well, that's okay. Just as there's one empty set with no members, there is one zero-dimensional vector with no coordinates. So yeah, we think there's one zero-dimensional vector. As an arrow, of course, it's not much cop. It's got no shaft, no direction, no head. But it does have a magnitude. So the square of its magnitude is the sum of no numbers. And the sum of no numbers is always best thought of as 0. So yeah, it's got a magnitude, okay, it's 0. Which means, so zero-dimensional space is just a point. And so the zero-dimensional vector is, in fact, the position vector of the only point in zero-dimensional space. And it doesn't need any coordinates to be that. So there we are. And not a lot there, but it's quite fun. Next time I'm going to go to something a bit meatier and think about different ways of thinking about functions and apply them to differentiation and, in particular, the chain rule.